Hey, I'm here to talk a little bit more about work and energy and some of the special cases that you might see. So let's just imagine a few scenarios. If you're on a flat surface, for example, and you apply a force to a box, and the box moves a certain distance, that work that you're doing is increasing the energy of the system, so work might equal force times distance. But the question is, what kind of energy are you adding to it? So keep in mind, in a flat surface, there's no change in height or elevation. So therefore, your potential energy is going to remain constant. Usually constant defined as 0 if you're on the ground. So any energy that you add is either going to increase speed, and if it's increasing speed, then you're adding kinetic energy, or you could be having friction involved, in which case you are adding internal energy. But there should be no change in potential energy whatsoever. Let's say instead of this, you have an inclined surface. And you can actually have all sorts of different kinds of work. But as this slides down, right, for example, gravity does work to help pull it down. But keep in mind that gravity pulls straight down while this thing is moving in a direction like that, so they are not pointed in the same direction. That means you would need, in theory, to use force components to figure out what fraction of gravity is pulling it down. And it turns out to be the weight of the object, F sub g, times the sine of the angle, theta. So your work would end up being your force down the incline, F sub g, sine of the angle, times the distance you travel. So gravity does work, but then the question is, of this work, what is happening to the object? Where does this extra energy go? Well, there's a couple choices. You could have, as it decreases, it's picking up speed, right? So you're picking up speed, you're also losing some potential energy. You could have friction involved, and if you have friction, you have heat being added to the system. So there are different options for these sorts of situations. If you lift something up off the ground, for example, you just lift it straight up. When you do work, the work is adding to the gravitational potential energy, GPE, or PE sub G, increases. You're not changing the kinetic energy at all unless the block is speeding up. So lots of different possibilities. Just whenever you see work or energy, keep in mind that they are connected, right? If you do work, something about the energy of the system is changing. If you're asked to find the work, you might just work from the energy and say, hey, I know it went up a certain amount of height. It went up that amount. We can figure out how much the gravitational potential energy changed, and that tells me how much work was done. The last thing I want to show you is a graph, force versus distance. So keep in mind, we said work is force times distance. This graph would be like two-dimensional motion. You wouldn't have things at angles like a lawnmower problem I showed you. So maybe the graph would look something like this, meaning there's a certain amount of time, let's say 1, 2, 3 seconds, 4, 5, okay. So I'm putting 1, 2, 3, 4 meters, and let's say the work represented is 1 Newton, 2 Newtons, 3, 4 Newtons. Okay. You want to figure out how much work was done. It would be simply force times distance, right? So For the first 3 meters, you used a force of 4 newtons, and you moved it a distance of 3 meters. Keep in mind that these are scalar quantities, right? So you can just simply add them together. For the next 2 meters, you used a force of 2 newtons, and you moved it a distance of 2 meters. So the work done would be 12 joules plus 4 joules for a total of 16 joules. That's one way to break it down. You can actually do it in the same way by looking at the area under this and say, hey, the area of this geometrical shape is equal to the work that you did. The force times distance. And you end up getting the exact same result because the area of this one right here, the one that I'm cross-hatching both sides, is equal to its height times its base, right? So it's height times base plus height times base of the different shapes. So the height of this is 4 newtons. The base of it is 3 meters. The second one has a height of 2 newtons and a base of 2 meters. So you still end up getting 12 joules plus 4 joules is 16 joules. So you get the exact same result for both. 2 different ways to do it. That's it for now. Thank you very much for watching.